Okay, moving on. The other part we have to worry about in climate modeling is, of course, how the warming occurs in the verticals, considering the atmosphere has a very characteristic background stratification in the vertical that is maintained, so warmer at the surface, cooling to the tropopause, and then stratosphere warming because of ozone absorbing the UV and so on. But under global warming, there's been observed stratospheric cooling, and it has to be explained, and the explanation is well understood in terms of the physics, but the physics is a little bit hard to explain the radiative balance. Okay, so if you think about a simple model again, assume that the stratosphere has an emissivity of epsilon strat, and it has an energy balance sigma t to the fourth, so it's emitting down and up as we expect for long wave radiation, so down towards the troposphere and up into space, and that has to equal the amount of energy it's capturing from ozone and what it is receiving from the tropopause, and how much of it keeps because of its emissivity. So the first term is cooling by IR emission from the stratosphere both upward and downward, which gives us factor of 2. This is balanced by the heating by the ozone, absorption of solar radiation, Q ozone plus absorption of IR coming up from the troposphere and surface, so IR up trop. After surface and troposphere regain energy balance with the new levels of greenhouse gases. So when you increase greenhouse gases, we saw already how the various feedbacks and so on happen, and emissivity of the atmosphere is reduced, IR of the atmosphere into the stratosphere, of the troposphere into the stratosphere is adjusted. So after all that happens, IR upward trop is approximately the same. Okay, so you keep that in mind, that you have some energy escaping from the surface, atmosphere adjusts to compensate for that to balance the incoming shortwave, so that doesn't change a whole lot. Increased greenhouse gases in the stratosphere cause epsilon strat to increase on both sides of the equation. So you have epsilon strat here and epsilon strat here in terms of what is kept of what's coming up and what is lost because of its warming. Okay, so however, however, IR trop is not twice as large as the normal climatological value of epsilon T4 strat. So the cooling on the left-hand side would initially increase more until tau strat can adjust to compensate. This implies that tau strat must decrease to maintain balance. Okay, so what does it mean? Essentially, let's say greenhouse gases increase in the troposphere. It has two impacts. Outgoing long wave radiation is bombarding greenhouse gas molecules like CO2, which is going to take them to an excited state, not necessarily increased temperature, just they have gone to excited state. But in the troposphere the density is high, so they keep colliding with other molecules and imparting their energy, which increases the temperature. So there are two components. One is the IR absorption leading to excited state, and the other is the collisions of the excited states with other molecules to increase the tropospheric temperature. So the energy that's being lost to the excited state is not available for the stratosphere, so you are decreasing the amount of IR coming into the stratosphere when you increase the greenhouse gases. The other is that the increased tropospheric OLR can almost escape through the stratosphere because the density in the stratosphere also continues to decrease, and this leads to net cooling in the stratosphere. Okay, so make sure you understand that this explanation is similar but worded a little bit differently, but the idea is that you expect increased greenhouse gases and tropospheric warming to lead to a stratospheric cooling. Okay, so let's move to some schematic of equilibrium response experiment where you are giving average. So you are taking the forcing here and you are going to transition it to a upper level, let's say corresponding to doubling of CO2. Then the average of this forcing where it's not increasing, let's say like normal climate or pre-industrial climate or counterfactual climate where the increase in greenhouse gas didn't happen, then you have the natural variability and the average giving you normal climate. When you jump the concentrations to a new level and suddenly increase the forcing, the response time is quite long, and the whole system has to adjust in terms of ocean uptake, vegetation response, warming, OLR changes, evaporation, the glacier melt, and so on. So then you integrate long enough, you end up with new equilibrium climate corresponding to the radiative forcing that we talked about. So the equilibrium response here is given by the normal climate to the temperature change corresponding to the radiative forcing. Okay, that's fairly obvious, but what is realistic in the real world is that we are never really in a equilibrium state, right? We came out of the last ice age, human activity started, agriculture, deforestation, carbon emissions, population growth, land use change, and so on. So the forcing has been increasing, especially since the industrial revolution, because of fossil fuel burning, and we are never going to be really in equilibrium. So it's much more interesting to understand transient responses where the increase of forcing is slow and steady but accelerating now. So the instantaneous adjustment, so typically 1% per year increase in carbon dioxide happens. Here we are showing the smooth curve. The temperature response to simple energy balance model will give you quick adjustments without worrying about internal feedbacks. But in the real world, we have the system that is adjusting with some response time. So this is what is of interest. How do we use it? Basically, we are using it in terms of what global warming targets to set. So we want to determine in the 21st century, is there any safe level of emission we can reach and hope to keep it there. So now the debate is about net zero and so on, but the accumulated carbon since industrial revolution obviously is going to be around for multiple centuries. So if we manage to go to net zero at some point, let's say even 2100. Many countries have already announced. Sweden at 2035, I think, US at 2050, China at 2060, India at 2070, and so on. So if as a whole the globe reaches not only net zero in terms of CO2 but also other greenhouse gases, then the simple model would give you this kind of a response. This is the natural climate that wouldn't change because we are not increasing the emissions, and then you have the transient response. So the temperature at the time of stabilization is going to be somewhere here, and the so-called committed warming is going to give us this additional warming. So why is this relevant? Basically because this is kind of the most practical thing we have to plan for, and those are looked at in terms of warming projections and the emission trajectories needed to accomplish those. So here we have looked at this before in other podcasts and other forms. So typically people are already beginning to focus on 2030 and how far off we are in terms of ambition gap or emission gap and so on. So if you look at global greenhouse gas emissions in gigaton CO2 equivalent per year, we are on this trajectory, and unfortunately as of 2021, we are already in 2022 as I'm recording this. We have not shown any serious downturn in total emissions. There have been dips in emissions because of COVID and because of financial downturns and so on, but we are headed back up anyways. So here is the 1.5 degree consistent emission scenario, which means we have to should have started decreasing our emissions, total emissions in 2020, which we have not done, and we have to be heading here by 2030, and then at some point we have to reach not only net zero but net negative. Doesn't mean we don't emit carbon dioxide, it's just that we have to take out more carbon dioxide from the air than we emit. And then there are other targets, optimistic scenario 1.8, again 2030 we have to be there. Pledges and targets are going to bring us here. If we focus only on what is going to be accomplished by 2030 as promised in the nationally determined contributions, then we're going to hit 2.4 degrees by 2100, unless we significantly improve on those. And of course the existing policies and actions are in the range of 2.5 to 2.9 degrees C warming by 2100 with respect to the pre-industrial levels of global mean temperatures. Okay, so this is updated in November 2021, which is fairly recent. So this is why the models have to understand transient responses like this and work out various scenarios with our models that exist. Obviously, every time we integrate into the future, we are making lots of assumptions, not only about how emissions will increase, but how technology will allow us to do that, how our food habits, energy habits, and transportation, etc., will affect these trajectories, and of course how population growth will also impact these scenarios. Okay, so that's kind of the situation. When we come back, we will look at the actual models and how the scenarios are created so that we can get to actual global warming models and look at how some of the projections are done, what kind of scenarios are developed by scientists, and how they affect the projections, and what the model uncertainties are when we look at the historical period, and how the models differ from each other in the future projections. We already looked at things like climate sensitivity. Obviously this also results in a range of projections for the same scenarios. So we talked about model ensembling. So typically can model ensembling is give us more reliable projections, and what are the contributions of scenarios themselves to the uncertainties versus model deficiencies or model biases and climate drift in the models to the projection uncertainties. All those are difficult questions, but considering climate impacts are already here in terms of extremes and so on, and the warming, heat waves, health impacts, impacts on food production, etc. If action is to be taken, then we have to use these models with all the awareness about the uncertainties, and we still have to make decisions based on those. So those are the challenges that one has to deal with. Okay.